is identical. However, there were certain things underneath the hood where we need to change some of the paradigms in order to achieve a better performance and better maintenance and new paradigms that came up in the last 10 years. So preserve what is good, prune what is unhealthy, and to keep the project growing and maintainable, not just for the another 20 years, but continuously over. So it's not a fixed milestone, but it is we want to get also into a process of a continuous renewal. So, I mean, if you have questions, I can talk fast and convey a lot of information. If you have questions, please stop me and ask questions. So there are like 2 microphones, one with Jens and one with Marcus. We can add. So what are the modernization goal? Of course, it's GNU Radio. It's not Apache Radio or like Simulink. We want to preserve the community and the integrity and the large range. But in order to preserve that community, it's very important to remain relevant, both from a technical but also functional performance point of view. I mean, whatever is good, if you're stagnating, you don't continuously improve, eventually people say like, okay, there's another toolkit that is more suitable for the job. So as Eric also mentioned in his keynote presentation, is like this is also like a good time to reflect upon what do we actually want to achieve, what are the bottlenecks, where do we want to move forward. And this is like beneath that, I mean, like obviously these are like high-level goals, but specifically, that's also the reasons why GSI Fair is investing to it. We want to be able to use it in the industrial setting, also like in public infrastructure, to keep it maintainable for a 24-hour, 7-day operation week. So that means we have to rely also, we should rely more on true industry standards. We have a lot of new users, so GNU Radio is used large in the academics, but also in the private industry, you have a high turnaround, like many people coming, going. So we have to see about what are the pain points to reduce the cognitive complexity so that people can get more easily into GNU Radio, use it, and say like, oh, that's a good tool. I don't have any need for any other tool other than GNU Radio because it does the job well, at least to, let's say, 90% level. And that means also reducing cognitive complexity also means like reducing the learning curve. So basically we want to be able that somebody within a couple of days, weeks, is able to make use of it as a user, but also being able to contribute in a meaningful way that is also sustainable and maintainable from the core maintainer's point of view. All while this is not standing alone, but promoting a collaboration and sharing of ideas and links between academia, government, science, and industry. So this is a bit of an outline of my talk. Why GNU? Why radio? I wish I would get like a buck every time somebody asked me that question. We probably would build yet another accelerator facility with that money that I would have gathered and hired, or at least hired 3-4 full-time software developers. Then I think part of it, to motivate again, why graph-based signal processing. I think for people who use GNU Radio, that's obvious, but many people from GSI, this is also part of our internal training, is to motivate why describing signal processing problems in terms of graphs is useful and why it helps, and then going, what are the goals, the changes that we applied, and then some of the views, preliminary, what could be the next steps on the technical side, and then some question and answers. However, this one, please stop me, raise your hand at any point of time. I walk through very quickly now. If you have a question, stop, say like, Ralph, please could you elaborate on this? And yeah. So, why GNU Radio, especially at FAIR? It's a very odd question. Why GNU? Why radio? I mean, GNU is just historic because it was a free open source project, and the GNU public license was one of the first common open source licenses out there. So people say like, okay, if it's free and open software, nowadays we would call it like open radio maybe. But at that time, people chose for GNU in reflection to that this is a free software which can be used by a wide variety of people. And one of the changes that we did to 4.0, or what we propose, is to make it in some parts a bit more liberal, still preserving this open source character spirit that GNU Radio always had, but also make it a bit more permissive to be used in an industrial or public infrastructure point of view, where going fully open source in all different parts of the project is not always possible. So we want also to get a stronger relationship to the industry and government labs. And yeah, radio, I think both Jens and Shahab explained it. Software-defined radio is typically, we describe this for the shift of traditional radio frequency or signal, and now new with GNU Radio 4, also event processing, implementation from hardware to software. And if people think about radio waves, they usually think about like some dipole emitter, radio station, TV station, that emit electromagnetic waves, which are encoded, and then you receive it upon this. But GNU Radio grew well beyond just communications, but is also used in radio astronomy, where some of the radio signals are generated by pulsars collapsing black holes. And at FAIR GSI, what you heard, we use RF both to accelerate particles, charged particles, so we have like small cavities where an alternating RF field is being used to add velocity or energy to the particle, but at the same time as the particles traverse to the beam, they drag an electromagnetic wave behind them, which at relativistic speeds is a bit like a pancake. So, and this pancake is proportional to the shape of the bunch. So obviously the bunch has a finite size. And if you want to look into the details of what is the size of the bunch in the beginning and end, looking at the electromagnetic wave spectrum is a nice diagnostic tool to measure the position. For example, if you have like two strip lines, or let's call them antenna for the argument's sake, top and bottom, by looking at the difference of the RF wave and computing the difference and the sum, you can compute the position. And if you do this at a high enough frequency, you cannot just compute the position of the center of the bunch, but also what is the position of the beginning, end of the bunch, or the momentum spread, so what is the velocity differences between the very fast particles and the very low frequencies. And this is an important feature for us at GSI and FAIR to measure, control, and optimize, and where we also use this data not just to analyze, but to feed back into our control system to improve the properties so that the particles have the right property that our experiments want. So how many of you know machine code or wrote like 8086 as machine code, like binary code? How many? Okay, 2, 3, okay. So you outed now yourself with your age. How many of you did, just keep your hands up, how many did assembler? So that is a bit more. How many did C or C++ to level, expert level? Yeah. Yeah, Ivan, please, and Matthias, please raise your hand, because they're two C++ committee members. They should know C++ because they define it. But if you look at the hands, not everybody knows machine code, and not everybody knows assembler or knows how to program in depth to a level that it's high-quality research software engineering standards. But we all need to still solve problems. So we need like tools to get the job done. And in order to communicate, flow graphs have always been a very flexible description, both from a very high abstract level point of view to express signal or even event type processing. And what we added now is to make this a high-performance signal processing toolkit where we basically put the existing GNU Radio on steroids and add new concept like StudSIMD, which is a parallelization, but also a modern C++ standard, while still preserving the use of Python and exploring also other platforms like WebAssembly so that you can write UIs that can run in the browsers, and support for microcontrollers and AI accelerators and TPUs. This is all very technical, but this is not a standing on its own. What also GNU Radio is more than 20 years of expertise in a large, diverse community, which is streamlined and should be ready for tomorrow. So part of it is not just because I wrote something, but it's because we share the same idea, same vision, and we want to move it forward. So that's GNU Radio in a nutshell, at least from my view. Please disagree or tell me if you have, if you think this goes too far or not far enough. Why is graph-based signal processing useful? There's a concept of mechanical sympathy, where basically you don't have, as a quote by Jackie Stewart, as a famous Formula 1 racing driver, who said, like, you don't have to be an engineer to be a racing driver, but you have to have mechanical sympathy. So what he meant was basically, more general, you have to understand and care how a machine is working, because once you know how it's working also in internal, you don't need to build a CPU or GPU, but knowing how it works in itself will help you to get a better performance out of your machine and out of your hardware. So, and that's where GNU Radio bridges basically between the low-level programming, where you need RSIE experiences, but also the high-level concept where you want to get a job done. And just to flash some highlights, specifically for hardware software, this is We have to care about CPU cache because being cache friendly means our programs run 10 to 100 times faster. You have to think about branch prediction, memory alignment, how to handle concurrency, data parallelization, SIMD, non-uniform memory access, and notably also putting a bit of knowledge on the graph topology. So because of how I structure my problem can help me to improve the performance. And I'll come back to that in some slides later. So this is all a bit abstract, but because I thought like let's show like a bit of a user case example. I mean, like I told you that we use with the electromagnetic wave of particles to diagnose their position and size. And typically, if you do it naively, you put in a 180-degree RF hybrid, look at the sum and delta signal, and then directly digitize it, which some people say like that's the best version possible. But if you want to look into structures that are very small in the bunch, you need bandwidth of 1, 2, 3 gigahertz, which is, if you work with an oscilloscope, you get down in the bit resolution to maybe 6 effective number of bits, where this differences in position, they vary only by 10 to minus 3, 10 to minus 5, so no chance to see anything with an oscilloscope if you look at this from this part. So what do? How to improve beating the ADC effective number of bits limit? We know from ADC, there are like 2 limits. One is the Johnson noise or thermal noise of the ADC, and the other one is the clock jitter. And even though the ADCs of the past decade improved, ultimately they're now limited by fundamental physical limitations. And normally the rules of physics are absolute. That's the law of nature. But let's take you a bit on a ride on how we can cheat a bit and get a better performance. So yeah, if you want to get a better performance, you can either do time domain interleaving, so basically putting several ADCs in parallel, but you will be limited by thermal noise and clock jitter. Or another approach is that you use the same principle that our ear uses, like the cochlear, that you do like an orthogonal frequency multiplexing or cochlear radio, basically where you say like I have different hairs in my cochlea which are sensitive to just one specific frequency, nothing left and right, but with a very high dynamic range. And our ear is capable to distinguish one frequency with a dynamic range of 170 dBs. So if you put 2 hairs, you can detect 2 frequencies, but with a humongous sensitivity. So why not split up the spectrum over several bands, put a detector on each one of those bands, and then basically we have the perfect broadband detector. Now, you can start building a flow graph, basically where it's just splitting the RF spectrum into multiple orthogonal frequency bands. This is just like a block diagram, how you would write it from an RF engineering point of view. And basically in this band, you get basically your classic SDR-style IQ signals, but now we do this like 32 times to cover the whole spectrum that we want to. And if you look now simulation, then you can say, because we have a finite bunch length, is actually you don't need to cover all the frequency in the spectrum, but only the characteristic frequency which is given by the pulsed RF duration that you have. And since our RF bunches are finite, you can get by just using a couple of bands where you need to look at, and then you get in blue the raw signal and in green the reconstructed signal. So this is basically a simulation, and it's basically like a Fourier decomposition. And if you look at the reconstruction error, it's less than 1%. So works. Then you start like, okay, the concept works, let's build this in hardware. And there you can see where the mechanical sympathy comes into play, because here you can see like some filters. So what we had before in the blocks, in the flow graph, you have like a hardware representation with input port and output ports. That's the reason why I also like the old GNU Radio companion with this input-output ports, because that resembled, for me at least, from an RF engineering point of view, very much to filters and amplifiers that you had. But you can follow the same structure in the hardware layout with the amplifiers and the detectors in the end, like you did in the simulation in the flow graph. Now, that's like an optimization that we also apply in the software. Once you know that it works, it's like, okay, I know I have my composable blocks, but I don't need all these connectors because each connector costs money, costs RF performance, reflections, length. Let's get rid of it, and let's cast everything on a PCB. And basically this and this are the same, but this is just a higher integration density, it's cheaper to build and can be mass produced. But still you can use the same tools to simulate the performance of this, to see whether it corresponds to this and the software side. So where do flow graphs come in? So you have like this mechanical sympathy where you have an idea, which you turn into a flow graph to design and simulate. Then you can, first in the simulation stage, to validate and improve on your design till you think you're ready. This is like the prototyping, also for new standards, being like 5G, 6G. And once you're happy with that, you say, like, let's make a prototype and turn this into hardware. And there are like two parts. So one part you can say, like, okay, I simulate the hardware, go back to the flow graph, or I say, like, maybe some parts I don't need hardware for. It's perfectly fine that I keep it in software, because there's a level of certain things are better to be done in hardware, certain things are better to be done in software. For example, this bunch reconstruction, doing Fourier transform and reverse software is much better than doing this in hardware. Also because of calibrations. And you say, like, you're happy with your prototype, and then comes the next big step, because your boss wants to use this like 100 times, or he wants to use it operational 24/7. Let's put it out on this fully integrated board. And this is the part where we presently hit sometimes like a roadblock in many industries, and nobody likes to talk about it. It's a bit like this, everybody likes to talk about success, but nobody about failures and about reimplementation. Many of the industries and many people we talked about it, whenever you transfer a prototype into real operation, also like in the software part, people say, like, let's keep the concept and re-implement everything from scratch, because we can't use the existing code base because of licensing or compatibility, or it's too heavy, it doesn't fit on a microcontroller or an FPGA. So basically people keep the concept but basically redesign the whole software stack for their operational deployment. In many cases, some people use also GNU Radio and satellites, but many people we discussed, there are many also that redesigned it. And on the software side for GNU Radio, one of our goals was to remove these barriers through either improved buffers, data types, so that we can both transmit unstructured and structured data, and to allow also like notably like low latency handling and merge API, which basically is the equivalent of getting rid of those connectors, which are expensive, and to make a more efficient use of CPUs, GPUs, TPUs, and so on. This is not a new idea. I mean, like now, GNU Radio started around 2000, and I looked at what was actually the first thing that ever used flow graphs, because I thought, like, okay, many people asked me, it's like, doesn't this awfully look like, depending on where your engineering background is, like either LabVIEW, because LabVIEW uses also graphical programming, or doesn't it look like Simulink or others? And then I thought, like, okay, who was first? And who do you think was first? Simulink? Simulink is like MATLAB and MathWorks, like these two big companies competing. Who was first? Who do you think? MathWorks, MATLAB, Simulink? Who says like Simulink was first? Who thinks LabVIEW was first? National Instrument. Okay, and the others are all undecided because I think it's a trick question. I'm not good in poker. You're right. You know the guy who invented the telephone, Graham Bell? He founded the Bell Laboratories, AT&T, Lucent, Comtel, I think now Vodafone. So this was like invented way earlier, already in the 1960s, and they called it BLODI, like a block diagram, where you can see they had already a flow diagram in the early 60s. And if you look a bit closer here, they didn't use the new GRC YAML model for describing flow graphs, but if you squint a bit, you see like, that's pretty much what we're doing today. Why did they do it? They said, like, because they built hardware, purpose-built modems and other chips, and this like, before we make very complicated digital communication systems where we spend millions on building ASICs, let's try it first in software, see whether it works. Then we can cast the filters, and then we build it. So they used it a long time to just simulate this loop. And I thought, like, and even sometimes in near real time. I thought, like, okay, there's nothing new under the sun, so let's see what we can learn out of it. And there were some iterations in Bell Lab, it's also continued being used, and then some guys somewhere in California, I think, if you're Berkeley, somebody said, like, oh, that's useful. They read this paper and said, like, could we extend it, maybe also low level, let's do this for circuit simulations, and they called it SPICE. So then, 1973 was SPICE, and then you have Simulink in 1984, in 1986, nearly parallel. You had both Simulink and LabVIEW, which basically followed the same concept. And then later in the 90s, the Germans, like Siemens, they also said, like, how do you do like PLC programming? If you ever heard what semantic S7 graph or PLC programming, they used it in the 90s. And also redesigned their whole processing framework on their whole graphical representation. So I didn't show like all the different ways. So there is something to it, because they say like, yep.
I was going to say there was also the stuff done at Berkeley around Copernicus project, which had a bunch of different graph-based systems also.
Yep. So it was very popular, and then I started thinking like, if you go back and say like, why do people use graphs? Because they say like, this is the best of both worlds. So you don't get lost in the details. You have like some people who know how to implement the nitty-gritty detail of doing correct simulations, correct data processing. And then people who say like, I have an idea of the domain logic about the physics, what I actually want to do, who don't care about how it's implemented on the underlying hardware. But they say like, I have my signal A that needs to be transformed from A to B. Here I have a feedback loop, and does it still work? And making prototypes. And this was extremely successful. And then GNU Radio, I think the main and the very important contribution from GNU Radio is publicly funded. And this added like this open source aspect to this, because all of the other ones, I mean, except of Bloody and Spice, I mean, like Spice was also like proprietary, but only became recently open source. They said like, if you want to use it, you have to buy our software, you have to pay licenses. It's very limited, you can't extend it, you can modify it. If there's a bug, you have to go in this. And GNU Radio opened it, being open for everybody to inspect, modify, so this true free open source spirit, and is vendor neutral. I think that's one of the big power, that it's not biased towards one particular architecture platform, but can be adapted to many use cases. Now you might think it's out-fashioned, but if you look, even like modern developments from Microsoft, Unreal, also game engines, they use the same concept still in large AAA game development and other systems, because they say like, if you develop a project for, if you just have like a project that you can develop with one developer, it's easy. He just hacks down the code that it needs. If you have 2 or 3, if you find like-minded people, they can still work together. But if you make a very big product or system, you have people with a detailed software development experience and people with a very high, let's say, artistic, physics, graphic design point of view. But still, all of them have to interact with each other and communicate. And this flow graphs is an exceptional tool for making complex things and dependencies simple. And yeah, now for us, we're just doing an iteration, taking the same concept and putting it on steroids, better performance, sleeker designs, and yeah, making it. We hope that this will help to make it a bit more liberal in terms of yeah, the LGPL, to make a library adoption, but also more useful for industry and public infrastructure. So this is like why graph-based signal processing. Now you will also like, okay, I know all about this. Just reflect a bit back. Now I'll go a bit on the stack further deeper down. So what were the goals, open source and the communities? I mean, GNU Radio 4, because we're allowed to do breaking changes. We try to make a reimagine or redesign which preserves the clean and lean structure, and then has like a modern C++ approach. And also we want to favor composition over inheritance. What I mean by that is, normally if you have a traditional prescriptive framework, you have like a framework house where you have certain blocks. You can exchange them, but all of the blocks still have the interface is the same change, and you maybe just can exchange the colors of your block. But it's not really flexible, because it still prescribes you, these are the interfaces, and you can replace this block, but if you replace it, it has to look like this, exactly like this, and nothing else. And we went for the route, more like a modular, library-based approach, a bit like Lego bricks. I think like flow graphs, everybody knows Lego bricks. I hope like you all had the fortunate childhood to play around this. Where you say like you have certain interfaces like the small nubs that they're interconnecting, but other than that, the blocks are completely free. They can have any shape, any form, any color, and you can composite and also use only what you pay, what you need. In this C++ mantra, you say like you only pay for what you use. You can opt, I don't like this block, I don't need it, throw it away, you don't have to use it, and can take a block from somebody else. So what is the anatomy of a block? And it's like, oh my God, you will be thinking like, I've seen this hundreds of times, but I think this was an important exercise that we had in the GNU Radio architecture group. I think lots of the work was also stemmed and coordinated by Josh, who basically went back and said, like, what are actually the important things that we want to preserve, what is important, and what are the pain points. And for the block, we said, like, the block is basically a pure stateful signal data processing function. You can have a setting expressed as class members or map type informations. And the block has to ensure that if you get certain data in, out, that the constraints are met so that the function can compute this input-output. Then you have a certain inputs, which we call now like streaming input ports. They're, which is a bit different to GNU Radio 3, they're always synchronous with the type T, which can be either a fundamental, like before, like integers, floats, and so on, or there can be structured data, which is new. So there can be structs like vectors, classes, or any arbitrary object that you might think about it. And the framework allows you to propagate this without any constraints other than the object has to be movable and copyable. Then the second thing is we added tags, and this is also nothing new. Basically, each of the samples or structures and messages can be added with a tag, where you can add some map type information, triggers, and new settings changes, which is maybe a new thing. If you have, for example, a sample rate, that you change the sample rate in a previous block from n heads to another one, that the sample rate can be propagated through the whole chain until the sync, so that the sync, for example, many of the processing doesn't care about the sample rate, but if you want to display it at the end, it's nice that you know, like, oh, this data was generated by this sample rate, so you can put like a proper y and x axis in terms of time, and you don't have to twiddle around what is the actual sample rate, so a bit more inbuilt safety. And this is mirrored with the streaming port. They're also synchronous, but what I mean by synchronous is that there is no additional delay or best effort, but whenever you get an input, you compute a function rate and then generate an output. But the output doesn't mean that the output has to be necessarily like a one-to-one sampling ratio. You can do decimation, interpolation. You can also do a dynamic ratio relationship between input and output, and including that you don't consume inputs, that you do not produce outputs, or you produce an output without an input. But the thing is, if you do normal data processing, you do this with streaming ports. And they're synchronous. We can flag them that the ratio is not constant, but that's maybe like a different constraint. And then we have message ports. In hindsight, we should have called them control ports, because that's also how they're called in GR3. They're asynchronous, they're executed on a best effort basis. They're normally used for changing settings or transmitting, let's say, protocol data or things that need to change on a not a fixed time scale. It can be used, and so on. And lots of work. Josh is a bit shy, but I think he did like a tremendous work with the prototype development and also the other people in the GNU Radio architecture group. Please raise your hand of all people who are participating in the architecture group. So like 1, 2, 3. So that's nearly half. That's one of the reasons why with this workshop we have to grow this group to be more people. But this was like was an important work to reflect upon what is good and what do we need to change. So how we modeled multiple computing domain. This is like via scheduler. So you have a flow graph, a global flow graph, and then you have sub-flow graphs, which are always assigned a given domain. That can be a CPU scheduler or like a GPU. And then you have basically a sort of an orchestration where you have a master scheduler, which is a bit like a orchestrator, like which basically delegates scheduling certain works on either scaling themselves, like a conductor, either scaling the works itself and said like, oh, please execute first sync 3 work, block 2, and so on. Or you can delegate to another scheduler, and then it has like another paradigm of how to schedule the work that needs to be executed. And this can change the priority. How you schedule work can depend on the domain. You can make it different for if you run on a CPU, and a GPU, a microcontroller, or an AI accelerator, or a TPU. So why is this useful? Because flow graphs, again, mechanical sympathy. It simplifies onboarding for new contributors to participate and contribute more effectively. Everybody looking at this can understand what the high-level concept you're talking about. Everybody can use then like common tools for very fast aspects like C++, or for plumbing you can use Python, or for the high-level aspects in the UI, for example, you can also use WebAssembly. And then you have basically two types of archetypes of people. One are the, let's say, what we call users, which have dynamic operational challenges, want to commission a facility or design studies or ad hoc prototypes, where they can modify this this graph to the liking, but when you put it in, yep. 40, yeah. The GNU Radio 3, I come back to that, it works completely different. Basically what we did, we, like this inversion from inside outside, before the scheduler was part of each block, most of the functionality, and then we said like, no, we remove everything that is within the block to schedule and make it a global entity. Yep, yeah. That was one of the pain points. You mentioned like when you do like parallel computing or with constraints, that you sometimes had a way to that blocks were competing with each other, and that was known. So we have on the one hand like the people like the racing car drivers who know what they want to win the race and want to solve the problem. But on the other hand, you have like this engineer who keep the car up and run floating. And that is basically also like maybe the definition on the difference why we split it up into tutorials, because the view on this flow graph is quite different if you use this to express a domain concept, if you use it for communication, or if you want to really improve the infrastructure that does the signal processing. So.
How do you plan on implementing RF-NOC compatibility in this framework?
I'll come back to that as one last slide, vision of the next two. Short answer beforehand, the vision is to invest more into SYCL. I'll come back to that, what it is. So that's the reason why we branched this in two, and the user tutorials are led by Jean-Michel. He also asked me that at the end of this talk that he wanted to have like 5 or 10 minutes to explain a bit what is the difference on what is being shown and explained on the user tutorials. And I think from this slide deck you can see what Alex is talking about in his part. So I'm just highlighting the top level, but this one is not meant to go to the very deep things. This is like then discussed in the different tracks, because for the people who are users, we don't want to bother them with low-level C++ and SIMD, unless they're interested, and vice versa. So this is led by Jean-Michel, and initially I thought like this racing car was a good example, but then I noticed when he sent me this picture, that's not a racing car in the background. So I think we have to change it to something more like this. So having like a low-altitude orbit. So basically all the people who attend his tracks are getting those spacesuits, and going to be the heroes and save the day. So now let him get into the meat. What did we do? The changes for GNU Radio 3 to 4. And we tried to simplify the C++ user API. If you develop blocks for GNU Radio 3, you know that you had to edit 3-4 blocks, that you needed the mod tool to instantiate the block, write getters, setters. And we thought about is like, can we do it simpler? So, and we decided like, yes, because we said like the scheduling is not part of the block. So this is basically the hello world. This is not slideware, this actually compiles. If you want to write a block, you simply state your block name, you derive it as a CRTP, that is curious recurrent template pattern, which is basically a template which inspects whatever you wrote in here. So, and this does like compile time reflection, and adds all the getters, setters automatically during compile time. That works very well, so that means you don't have to write any more code, but the compiler has to work a bit harder, and that's also why I have to apologize why some of the compilation times are a bit more than what you had in GR3, for example. But it's worthwhile, and I'll come back to it later. But if you want to write a block, you just specify an input port, an output port, and here you have a setting. For the time being, you still have to use a macro enable reflection where you announce what needs to be exported but now the compile time reflection is nearly voted in, so it's very likely that it will become part of the C++ 26 standards. I'm hammering on Matthias every other week, where it's like, and by the way, I'm of the opinion that compile time reflection should become part of the C++ 26 standard. And now more and more people chimed in, and it seems to become a reality. So this is not just a future possibility, hypothesis, but it's like possibility. And then everybody knows mathematical functions, and the simplest thing that you have to do is just implement one function, which is process one, which takes one input sample and produces one output sample. In this case, basically takes the input samples, multiplies it with a scaling factor, returns it, and then that's all. Nothing more, literally. And we thought like you can't do much wrong. The only thing what you can do is like write your implementation factor. So we hope that this style of API should simplify block development. It's also much easier for functional tests because you don't need to build a whole flow graph to make sure whether your processing is correct, but in the end you just need to make sure that your process one function is implemented correctly. So the unit testing becomes easier. Because it's a const expert interface, there's no virtualization. That is because of the CRTP pattern. The compiler can see a much larger scope of functions. And that allows the compiler to do better optimization and merge some of the blocks already on the compile or functionality in the compile stage. And if you're like people writing C in the 90s and you see like, oh my, come on, this is like so inefficient doing like a sample by sample processing, you'll be surprised. I'll come back in a slide later. But it's much easier to also to do like an early error detection because the scope that you have to reason about is very small. And yeah, Alex is going into the detail how to use that. We also added SIMD out of the box. This is basically part of the standard implementation, and where we have some convenience method that will become part of the libc++ that Matthias Kretz provided, and then basically of automatically parallelization over the different instruction sets that your CPU provides. So he's going to talk about this in detail. I can just highlight the top levels. But many people will maybe remember the process, the work functions where you get a certain input stream in and out, which is still possible, where you can get like an array of input samples, an array of output samples, also multiple input outputs if necessary, and then you can still perform iterating through inputs and outputs over those arrays. However, what I would recommend is, and this is like a talk that Simon and also maybe Alex will talk about, is it's much more efficient to use C++ algorithms and ranges because they have already built-in optimization in the compiler. So if you use these structures, the compiler knows better how to optimize it, and it can optimize better than your handwritten code. And yeah, fun fact, beware of premature optimizations. When I saw the process one, when Matthias introduced that, I said like, come on, this will be horribly slow. And my gut feeling said like, that can't be right. And before you start optimization, before you start using this process bulk function, if it's not necessary from a functional point of view, start with the process one, because in many, many cases that we tested, the process one function is actually faster. And we have some benchmarks to back that up. And the rationale is because the compiler has a reduced scope that it can better exploit and compile, and it's also more cache efficient because you have a smaller code section that fits better in the L1, L2, and L3 cache. I think I skipped that. Yeah, you have also like a way of automatically documenting the block. So basically the code is single source of truth. So you can add just a small description, and this is later used automatically without any doxygen or any other code annotation to derive documentation how the block is working. And this is like a pre-production code example for an FIR filter, for example, where you have also like a callback functions like settings change, where you say like, I don't want my settings updated without a validator, or where you have like some other complex dependencies that you want to apply and test before the settings are actually applied to the block. And yeah, self-documented code is single source of truth, and based on that, you can basically generate a printout example without any other tooling, just using C++ templating. Okay, this is like something for people who just use small installation or like prototyping. You might think like, okay, I have one set of settings, and they don't change. And if I need to change them, I stop the flow graph, change the settings, and restart it again. In our case, the systems are running 24/7, and we're not just having one use case, but we have multiple users using the same SDR hardware. So we have to switch rapidly between different modes of operation, producing one iron species, producing uranium, argon, protons, and switching back and forth. But we still need the same pre-processing for all of them, but with different gains, for example, or different filters that are adapted on the given use case. So many of the hardware devices are not exclusive. So then we have like two use cases. One is without feedbacks. So there you can say like, okay, for this use case, you can just operate multiple parallel signal processing pipelines or graphs. But as soon as you have feedbacks, that will not work anymore because you can have only one system that drives the hardware. So you need then to reconfigure the whole feedback loop in an orchestrated manner. And this is particularly important for us. This is like our tube map or subway map, where you can see like you have a Unilexus 18600 AGSR, and depending on the modus operandi, is a bit like Tetris. Each one of them is executing a certain mode of operation and then rapidly needs to switch to another one and back to another one, and yet. So we have a device that looks in the sys18 but needs to be reconfigured every other second and back and forth. So this is, for example, different settings when we accelerate. Jens explained the synchronous nature, that we have to ramp up the magnets while changing at the same time the frequencies, changing gains, and this is like how we model that. This is free of charge. If you don't need it, you don't pay for it. But with this optional multiplex block settings change, you can basically flip between settings, like a good setting, bad settings, on the fly using this context, special context tags. And this allows flexible multi-mission and multi-user operation. How does it look like? You might think like, oh, I need to implement a lot. No, most of the stuff is done implicitly. So basically, if you do a different set, then these settings like scaling factor are exchanged automatically in between the next time you're being invoked. And you can declare like a context variable where you can say like, okay, what is, as an info, what is the present context I'm running on, if you want to make some special magic based upon that. So this is like a simpler API. Let's talk a bit about performance improvement. One was the log-free buffers. So we all want to improve latency, bandwidth, and throughput. This is just like a small picture to explain the differences, but I guess we're all familiar. Latency is the delay between the cause and the effect. Throughput, the amount of material that goes through. And the bandwidth is the maximum rate of data or compute that we can perform. And if you need lower latency, we either have to maximize our I/O bandwidth, or memory bandwidth, or compute efficiency, or we have to minimize the data that has to go through this pipe and compute sections. So concurrent and parallel, basically concurrent is basically that you have different streams of execution, but not necessarily parallel, and parallel basically you interleave with this. And there, it's also like for the latency, it's basically the longest execution that you need, and normally we want to have this as small and deterministic as possible. There's an excellent talk by Jill Teen from Azul, how not to measure latency, that goes a bit more into detail, and I put like a PDF and a video link, YouTube video link on that. Yeah, mechanical sympathy, know your hardware. You all know how, maybe have seen this picture before. This is like how a CPU die looks like. You can see like here highlighted. I mean, it's not really colored. This is like a post-processing. I think the guys from AMD added that because otherwise we would not recognize it. But you have multiple cores, multiple memories. Some are L1, L2, L3 cache, some are shared. Then you have sometimes multiple dies that communicate across each other. And how you implement the code determines how efficiently you can use this hardware, or whether you have to do certain computations multiple times just because of synchronization and inefficient structures. One of the ideas is like, this is a bit like can't go too much into detail. This is a bit like a nutshell. On the lowest level on the CPU core, you can compute the fastest, but you have very small L1 cache. And then the higher you go, you get more cache, but usually it becomes slower. So the idea, if you program something, you want to make it as cache-friendly as possible. That means make your code sections as small as possible, as optimized as possible, so that everything can happen here in the yellow part. And only go up to the higher levels, complicate your code if necessary. And for this, having template programming and modern C++ and GCC and Clang are key to that. Yeah, there's also like, if you want more detail, there's like a tutorial on this aspect. So why is this important? Because one of the pain neck is like that why we want to just compute samples, that when we switch between the different tasks that we have to execute, there's typically like an overhead. So the old model for GNU Radio 3, each block was also a thread. So whenever you spawn up a thread or you need to start for the thread, you have a context switch that takes a certain amount of time. You have a systematic overhead for checking how much time do I need? Can I actually execute my work functions, or should I just return back to sleep until I get more data? And then if you add these again up to parallel execution, you see like from the original latencies, all these tiny amount of context switches and systematic overheads add up so that your overall latencies become bigger. That's a fundamental limit. So that was one of the way that we try to tackle is how to get rid of these small blocks, because they're now unavoidable. Are they really necessary from a compute point of view, or can we just drop them? And yeah, to give an idea on what the overheads are, some cases it's just like a microseconds, up to 10 microseconds. So this is like for thread switch, context switching. But even like if you go from the caches, we're talking about tens of nanoseconds to 100 nanoseconds. So the question was like how to get rid of it, because even if one classic paradigm is, in order to get rid of this overhead, this is Amdahl's laws, people's like, don't worry about this, just call a thread and compute 1 megabyte of data, then the proportion of this context switch and this checking whether you can execute the work function doesn't matter anymore, which is true. In terms of throughput, that's a good, valid approach. They say like, compute more without interruption, you get a better performance for throughput. But at the same time, if you say like, I want to compute 1 megabyte of bytes, you have to wait longer, so your latency is larger. So if you need somewhere an answer which comes in a millisecond, this is orthogonal. So in the end, if you want to have short latencies, you have to tackle this. And by tackling also this overheads, your throughput automatically becomes better. So we wrote a new buffer. In the nutshell, it still used this POSIX double-mapped M-mapped buffer that Eric mentioned this morning, where some of the resident C++ experts actually tell me that is possibly, but probably, or very probably, undefined behavior. So we're using a feature which any future GCC version might just remove the carpet underneath your bottom. But it's still the default, but you can also opt for new alloc strategies, and you can see that the difference is not that much anymore. And what we did is like we added this possibility of adding tags to minimize that interface. But in addition to the unstructured data types that we already had in GR3, we also added structured data types. And this can be, for example, from John Saleh's PMT map. This is like a polymorphic type map. Or you can use vectors, you can use tag, or we have new data format like packet, tensor, dataset, or whatever other struct you think is useful for your application. So, and with these buffers, there's several ways. You can have a fan out, that's the classic way, but you can also do a fan in, so it's also multi-producer, single receiver, or multi-producer, multi-receiver, or if you want to, you can even pass through when you say like, I don't need the data, I just want to look at this and I don't want to copy. This we tested just conceptually, but in the end we built it back because we didn't have any real use in-house for that. But you could write a block that makes use out of that. So bottom line, this is like a drag race. It's a very artificial test. This is not like a full workflow test, but just to see like what is the throughput, but on the same ground, producing samples in and out. How long does it take? So in red, the red corner, you have GR 3.10 with the circular, with the virtual memory buffer, and with the simple one. And on top you have GNU Radio 4, and you can see like you have up to a factor 10 improvement. And the main ingredients is because it's a lock-free structure. So whenever you read and write, you don't have to look for a mutex. But if there's no data contention, it's free. So if you once the CPU knows there's nobody else writing on the memory segment that I'm reading, it doesn't kick in the lock and no synchronization of atomics. Lock-free uses atomic compare and swap paradigm. This is like for the C++ experts. And by having strict typing and const export functionalities, the compiler was actually able to optimize larger structures of the code and remove the virtual interfaces, which got rid of some of the overhead of the existing implementation. But if you don't like it, write a better one. You can exchange it. It's modular. It's not contractual. This is now the performance. If you look at how many producers against how many consumers. In blue is the new log-free structure. We can have an interrupt service routine rate of about 30 megasamples or 30 million interrupts per second to handle in the simplest case. But you can see, especially for many consumers, that the log-free buffer outperforms it by order of magnitudes here. And only when you get into the range where the readers actually have to wait on the writers to produce data, you can see that they both approach asymptotically the limit of the number of cores. So you can see like a small diagonal line. That is where not enough threads are available to compute. New data structures, I'm not going too much into detail, maybe Alex is hinting at it, but before you could only transmit fundamentals, but now you can say like this struct, your buffer contains this data set, and then we made like different subset. A packet which just contains the timestamp, some data, and some meta information can be stripped, or you have a tensor which has also a bit information on. A tensor is like a fancy mathematical way to express vectors, matrices, cube volumetric data, and so on. Or you can have a data set which is very similar to the HEP, high energy physics equivalent of event processing, where you have also lots of other heterogeneous data being stored and meta information. You had a question? Okay. So why do we need it here also specifically at Fair, GSI Fair? So having a continuous stream of data is normal. Then we annotate it with tags, with context information, or like some trigger where we found like, oh, this sample is interesting because we found an edge, transient, or something like else. Can apply it to an FFT, then this FFT can produce a vector, and then group it alongside this tag, and then, for example, transient detector can filter out only the vectors that have actual triggers, and then you can process it further and put it into storage data and analyze it. And this concept is similar to the old PDU concept, but with the difference is that you can put in any data type. Like you don't have to mimic, say like, okay, this range of bytes is my vector data, but you can put actual vector data or packet data in there. Or you can group them and add additional meta information, then it's basically your data set. Or what you can also do is that you do a context matcher that is like, please give me, I have continuous streaming processing, but I'm just interested in certain parts of your transmission between the start and stop, and you can put markers there, and then have a matcher filter that basically extract on this context only certain subparts of your data, and then propagate them as data sets into a sink. And then you have different ways, multiplexed with start-stop, just with context 1, or if you just look on the transient, or you do just continuous monitoring, and so on. And this way you can build like very complex flow graphs. Maybe my microphone is not. Okay. Can still hear me online? Yeah, maybe. Where you can do also like more complex operations, not just on samples, but on those data sets, on this high-level mathematical objects, and do transient detection there. And because we are not, we changed the way how buffers and how the schedule works, we can also now support feedback loops, so that you can say like, please compare my new sample against the sample that I had previously. So here the main takeaways is now we can also use to process structured event type data, like packets, data sets, or like HEP style events, support feedback loops, and we have context dependent settings that you can get around. And this is also like a scheme. I mean, like this concept is not very new. You have this also like in other domains. And the idea is that we build up now an ecosystem with also high-level functions and flesh out these blocks that we can make these control loops work, similar to other known graph processing tools, tool chains. So SIMD, this is like a very extensive subject. And please forgive me if I have to gloss over. I think Matthias is, or Dr. Kretz, I said a doctor only for people who really deserve it, and he made his PhD on that topic, so he deserves this for sure. Has a very detailed talk on this. So I can glance just over a bit over of the features, but an important thing is because we removed virtual inheritance and moved to strict typing and templating concept like the CRTP, we've been able to allow the compiler to do much larger section of code optimization. And here's like an, let's say, a structure where you have a base class where the other derived class inherit virtually. And you can see here that every virtual interface creates basically a barrier that the compiler can't inspect because it has to assume, yes, we share all the same base class, but your implementation, you might exchange it during runtime. And the compiler can't know that. So it says like whatever is virtual, I can't go beyond that boundaries. That is, let's say, good in terms of compile time performance because you have your small section. It has to worry only about 10 lines of code. But if this 10 lines of code is executed 100 or 10,000 times, it can't see this recurring loop and not optimize for it. And that's this overhead that you have in processing and processing also over this bulk, previously over this sample by sample interface. Now with this CRTP concept that we added, this is basically in a nutshell how it works. The compiler can see through and say like, I'm not stupid. All what is basically the functionally is the same left and here, but the compiler sees through and says like, come on, you don't do anything. I just return 1. Why do you trouble me with this? And that's what we want, because if you have dead code or things that are the best computation or the best signal processing is the signal processing that you don't have to do. Or the best buffer is the buffer that you don't need. So what is the best buffer performance? The best buffer performance is when there's no buffer required. So one of the advancements that also Matthias introduced was like this merge block API, where basically like, let's get rid of the buffers and the ports, just glue them together, and then just say like, okay, I have an input buffer, and then I compute block 1, 2, and then the sync in one go, and then the compiler can optimize over these 3 functions and get a much better performance out. So this, I mean, this is optional. You don't have to do it, but if you see that a certain functionality is recurring or is very minute, you can merge it together. This omits the buffer and facilitates a larger scope of compiler optimizations. Also reduces the memory footprint, and that's more efficient use of the different caches, smaller code sizes, and which is also important because code size is also kept in the cache. So less code, the faster it runs. And yeah, the target, and we have some proof of concept that we're able to run on a microprocessor, for example, on a Raspberry Pi 2040, that's the Pico. So we're talking here about microprocessors that only have 2 megabyte of flash. So that's the limit that we got. We have to work a bit on the user experience because if you're in a microcontroller, there are lots of other constraints. You don't want to do printouts because most microcontrollers, for some reason, don't have a console or they don't have threading even. So in the proof of concept, I had to manually disable the threads and the printouts, but we want to make it automatic when you target for microcontroller that only the absolute minimum is compiled in. And yeah, we hope that this facilitates an easier transition from a flexible R&D prototyping into production use. So SIMD, I mean, like we all know, basically we have a certain set of instructions and certain data, and then we have like some magic that does some mathematical performance operations on the instruction data sets, and then you get one result. And then you can streamline, rinse and repeat, but most CPUs, to get faster, they can't increase the clock speed anymore because that's the thermal limit they will reach, so most of them clock out at 5 gigahertz and only for short times. But the way the strategy that was in now for the last 14 years is to go parallel. So basically SIMD, where you have multiple data, you have the same operation, but you say like, let's execute this on a larger chunk of data and then get all the data out. And this is still executed in the same clock cycle. So when you had like 1 instructions per clock cycle, then now you can have like up to 4 instructions within the same clock cycles, and that gives a factor 4 views. And if you don't use that, basically your performance is as slow as Python. So you have to interpret every assembler code one at a time. And if you want to be fast, you have to use this vectorization. I mean, there's some libraries like Valk, for example, that did already some kernels that optimized this, but this is now more and more streamlined to become part of the C++ standard, so where it will not work just for one architecture, but for any architecture that the compiler is being designed for. And I think that's a very powerful tool. And that's an aspect that Matthias is going to talk about. Now, how does it work? Okay, I'm not reading through this, but there's a big shout out to Matthias, who adopted us a bit and said like a very nice guinea pig, and who drives this also at the ISO C++ committee as a subgroup group 6 numerics chair. But you can see, for example, if you have here's a bunch, it's a benchmark from simple flow graphs. So from a source to sink, source, a copy, sink, source, with a constrained number of samples, and then some processing which have certain limitations on how many samples they can consume or produce, up to something like multiply by 2, divide by 2, and then add -1, where you would normally say like, okay, times 2, divide 2 is stupid. That should cost, I shouldn't waste any CPU cycles on that. And then to make it even worse, we said like, okay, let's do this 10 times, just to accentuate that I have many long chains of simple operation. And then you have one, let's say the runtime performance, which is like about 80 megasamples per second, so it's still performing well because of the new buffers. But if you merge it, you get to 250 megasamples for free. So that is significantly faster. And for the other optimizations, we get even up to the realm of a few gigasamples per second that we can compute on the CPU. This is just compute. Don't mistake this that you can now do, when you read like 5 gigasamples, I can do my 5 gigahertz. I don't need an FPGA or DSP anymore. You still need the data out from the device into your RAM. So this is basically performs when most of the data is kept nearly always in the L1 or L3 cache. But what you also can see here is the same times 2, divide by 2, and -1, once with the process 1 implementation, one with the process bulk. And we made it fair and made the best optimization that we can do. And what you can see is, the box is unfortunately a bit misaligned. You can see that the process 1 is significantly faster than the process bulk. For me, that was something I had to swallow along, because I was used for decades to write low-level C++ system code, even to write assembler code and machine code, and I thought like nobody can beat my assembler. I knew nobody could beat my assembler. I stopped in 2006 because GCC produced same quality of output in 10 minutes what I needed like 3 months to write. So I stopped writing assembler in the mid-2000s. But for that manual loop unrolling and those tricks that we all as C or C++ developers are used to use, when I saw this, oh, this is not true anymore, that took some time to unlearn. To say like, okay, this is a habit that I acquired over 20, 30 years. It's like, that's not true anymore. Because compilers, especially for larger code bases, they're way smarter and can see much larger scope of algorithmic complexity than humans can do. They can see also potential optimization that we haven't thought about it, that by reordering, because C++ or C, any modern CPU, doesn't execute code sequentially anymore, but is also allowed to execute out of order. This has to do for performance reason, and many of this out of order execution make the actual code that the CPU runs look much different to what you think you're writing. Bottom line is, avoid premature optimization. First, write a code that is logically, algorithmically clean. So if you can cut down a numeric complexity from O(n) cubed to O(n), that's a much bigger gain than you get by this micro-optimization in C++. And this, I will talk about this more in the last tutorial in the programmer's track. So yeah, let's talk a bit about timing. This is like this 2 o'clock problem. How to synchronize about multiple nodes. Particular at GSI Fair, we have a massive multiple input, multiple output signals, and normally if you want to synchronize them, you're trying to keep every receive channel on the same data acquisition board. So if they all run on the same board clock in the same ADC, or the same set of ADC that run on the same clock, that's the best way to synchronize it. However, this is not always possible. For example, at Fair, we have some systems that are distributed over 4.5 kilometers, so we can't pull cables and keep the signal fidelity over 4.5 kilometers. But also, we have a channel count in the order of, the raw channels in the order of 3,000 to 4,000 signals. So there is no duck with 4,000 input signals that can sample at 200 megasamples per second. So you have to synchronize it somehow. And this is like this 2 clock problem that Eric mentioned. Yeah, how do you do that? Maybe Simon implemented it now. Basically, the idea is that we made a inbuilt integration for timing synchronization. The main thing is that we use tags to synchronize data streams. So we abstracted the timing synchronization through generic block, which could be wide rabbit timing receiver, could be a GPS receiver, or if your slow timing is enough, via UDP timing receiver that sends out synchronization methods, or has a hardware link to your actual digitizer, and then basically it adds a tag to the data stream, and with this meta information that comes through, it says even like that's the pulse per second, or the UTC time, or whatever other information you want to put on it. And if you do this across multiple nodes with the same timing source, for example, wide rabbit, then you get data streams depending on when you start the node. You get earlier data or later data, but you have a unique alignment. So this circular buffer has to align, so this comes at the cost of latency. And so it's like I hold the data until I have 2 matching tags. And then I can count back and say like, okay, I can emit the data. And then you have to handle with the corner cases. If one clock is slightly faster than the others, you have to choose what do. Do you interpolate? Physicists hate interpolating data, so because it's fake, we don't make up data, so we drop the channel that has too many samples. And yeah, Simon did a very nice implementation handling all those corner cases, so that after the synchronization block, you are sure that the rest of the flow graph is executing synchronously. And the synchronization also works not just on the receiving end, but also on the sending end. And yeah, this is solved through standardizing the tag through default tag names like trigger name, trigger time, trigger offset. So now, let's say maybe the biggest thing that we changed. This is the most important things why Josh and others started this big 4.0 revamping was like to rework the schedule to make it a bit more flexible and to address certain pain points. So the 2 limiting factors in the GR3 design, this were mainly let's say call them the main pain points and reason why GR4 development was started, is all blocks are also threads, and their processing function is ultimately managed by the system scheduler. So that is basically by the same OS scheduler that runs your graphics card or your other blocks. And on that level, all the GNU Radio blocks compete basically with each other and also system tasks for the resources, for the computing resources. And then you can have issues with starvation, non-determinism, or other blocks that are not non-embedded or microprocessor friendly. And also a lot of the latency is defined by the maximum minimum buffer data intake is not globally controlled by default. So basically the latency is defined by how many blocks and how many buffer sizes you have in the input. And this creates undesired latencies and also a larger memory footprint than needed. So how does it work? This is like a simplified flow graph. Just ignore the constraints on the bottom for the moment. If you have a source, block 1, block 2, block 3, and sync, let's assume that the processing function takes the same time for all of these blocks. If you want to have some samples in the sync, you execute source 1. It fills up the buffer to the brink until it says like, hey, I can't execute anymore. Then you would inform the buffer, hey, I have data. Then the block 1 is woken up. It always takes the same data, and depending on how big the data is and how much the buffer is, it propagates it through, and then you get like accumulating larger chunk of data where basically the smallest buffer in the chain will, actually it's a combination, will determine what the latency is until you get a sync. Now, if you add certain constraints, and it's like, hey, my source produces only 1024 samples. My block 1 cannot consume more than 128. Block 2 can only produce 1024 at a time. And block 3 is like, well, either 32 or up to 128. I take whatever in between. And the sync questions like how many samples will arrive there. So let's play a game and let's see how this would play out in a scheduler. I simplified it a bit. I ignored the contribution from the source and so like the source is executing, has an overhead because of the context switch, checking, am I allowed to run? So like, yes, and I produce data that's with a solid thing. And then it says like, let's call block 1. And because I produced 1024 samples, and I can execute 120, I can consume 128 samples, and says like, yes, it's okay, I can produce 128 samples. But now the problem starts, because if I go to block 2, it's like, nah, I need 1024, and you just gave me 128, go back. And it goes back to sleep. So block 1 goes back and says like, okay, I have still a buffer in the input, let's consume the next 128, goes back to, block says like, now can't do, block 1, block 2, goes back and forth, until you get like this 8 time through. And then basically block 2 could produce data, but because it acknowledged, it also notifies the sender and says like, hey, I got data, do you have more? But block 1 says like, no data, so you still execute the block 1 without actually having a chance to produce data. Now the same thing happens with block 3. You go block 3, sync, and then you go through. And if you count, that's basically the sequence. That's the earliest time that the sync actually gets samples. So if you look on the earliest day you get data, you have a latency of 19 cycles, plus all these overhead. Do you think this can be done better? I mean, if you look at the scheduling task, you're just one guy, how would you execute it? You would probably say like, let's produce the data, and then I know this block can't work until it has 1024 samples. Then let's execute block 1 8 times. And only then execute block 2. And then the same, execute block 3 8 times, and then sync. And then you have basically the most efficient way how to execute it. And that's basically the ideal sample. And then you have basically the throughput is optimized. You have much shorter chain, much quicker to your result. And even the latency got lower. It's not much by 1 cycle. So you get your data 1 cycle earlier. However, if you say like, I want to get earlier data, then you can select, okay, the first time this block 3 produces data, I go to the sync, then you add it here, and then if you say, I take the same flow graph, but I want to optimize it for latency, I get my first data, my first sample out already in 11 cycles. And that is an information that GNU Radio 3 had a hard time to optimize for, because each of the block didn't have a knowledge on what were the constraints from the previous block or the blocks behind. There was, by default, there was a very interesting talk by Matt Attis, like at the GRCon 2019, where he talked about this issue. This is not, I'm not telling something new. All the in-depth people know about this. And they say what can you do? You can shrink the buffers, and there's several ways how to do it and how not to do it. Even he said for as GR3 is worked, you shouldn't do this because of certain caveats. But what he and Derek implemented this, proposed is basically, let's put like a gatekeeper. So you have your chain, you have your data, your vector source. You send your data out through a long chain, and then you inject a tag, and you see like how long does it take until the tag arrives at this final block. And only once this block receives the data, it sends a message to the gatekeeper in the beginning, so like, okay, now you're allowed to produce more samples. That works, but still has this problem with the overhead that you need to ping each of the blocks. So you have this ping back and forth for each of the blocks. But it is a way to control latencies. It's a valid solution, but it's on the user level. So if you want to schedule this for different sub-topologies in your graph, the flow graphs become very messy. And what we did is basically the scheduler does the same approach, but implements it not as a block, but as a semi-global schedule, like a orchestrator or a conductor that says like, okay, I know about the topologies. I inject the knowledge of the constraints which I can inject in while the flow graph is being constructed, and I can ask to make this to take the topology into account. So basically, it's just an inversion. We remove all the scheduling information largely out of the block and into a global scheduler that basically orchestrates which block is executed in which order. And the importance is also like the optimizations that we could do there, because in the end of the day, if you have 1,000 blocks, but only 4 cores, you can't execute 1,000 blocks at the same time. but you have only 4 cores. You can only execute 4 cores at a time. So by using threads, you have an unnecessary overhead of putting the thread into a core, getting out, in, out, and then you lose performance. But if you know that you have only 4, you can say like, let's keep just the processing function in my global shared queue, and then dispatch it to whatever core is available. You can have either a global queue or local queue, and can basically optimize it on that level. And that is most efficient because it minimizes this context switches and also the need for triggering the branch in terms of branch prediction. Default branches where it's like I call a block, even though I know the block will say like, no, sorry, I can't work with this. It's not enough data. Yeah, we still need to be mindful that we need a distinct scheduler. For example, for the CPU, there you have like a default, fair, real-time, or one. Typically here you prefer smaller data chunk sizes to process because you want to keep the data within the cache and also to optimize the SIMD performance. But for the GPU, for example, if we need to transfer data to the GPU, the data transfer is very heavy. You don't want to do sample by sample, but you want to do larger block size. And that's the reason why the GPU has to take more data in. And then for each of the domain, be it CPU or, for example, in this case, GPU, you can implement different scheduling choices. For example, you can choose a global versus per thread or core work schedule queue. You can use CPU shielding or schedule scheduling and all the other different techniques. Now what we did is, just to illustrate for argument's sake, we're not going through all the cases, but here in the top we had like this simple flow graph, which is, I put like a imp and an angel, because these topology were specifically designed to trip schedulers, which are hard to solve with the existing scheduler, but where we wanted to put it out as a challenge. So the question is like, what is the correct, best, and most efficient execution order? The thing is, I can't tell you that is the best scheduler for all applications, because there is no single one fits all solution. So we proposed like a certain set of topologies, like blocks with parallel branches, blocks with feedback loops, blocks with multiple outputs where you can check on how do you optimize the latency from the source to the sink, or throughput, or doing this type of structures, which look a bit weird, because I mean, for GNU Radio, most people are not used to seeing feedback loops, but this is a very common topologies for neural networks, where basically, or recurrent neural networks, where part of the output information is put back into the input, and we apply inference or model learning. So what we did is, just as a proof of not concept, it's like a default implementation, but just to show what is possible, we have like 3 scheduling policies. One is like busy looping, depth first, and breadth first, where basically you get to different strategies how you traverse the flow graph. But there are many other possible solutions, like topological sort, critical path method. There's a whole region or a whole area of research, active research being done. And you can have a look at the README to see through the list. And people can have a look at it and see like what is actually best. We don't know what is the best topologies, but one of the next step is to start now with the API, to start like a sort of a GNU Radio competition to find the best default scheduler that's good for the vast majority of users, the best real-time scheduler that optimizes for latencies, the best throughput, and then have like a friendly competition who can write the best scheduler, for example, for this set of topologies that we have outlined before, and then benchmark it, and then see like who wrote the best version, makes it as the next, like a patent, like the next GNU Radio 4.0 scheduler in. In any case, this is modular. If you don't like a scheduler policy, they can be exchanged. So it's like, nah, I still use my own. The level of getting into it is fairly low, but it's technical. That's the reasons why we said like we needed a dedicated developer track, because it's not all scheduling aspects are for the faint-hearted, unfortunately. So what is next step? I mean, like there's several domains like community engagement and advocacy. This is very important. I mean, like as much as this is about technology, it's also about people. I mean, like if you have a team of 1, you're always in agreement. You have the best and worst ideas at the same time, but as soon as you have a large group of people we have to find support and share ideas and also reach a common goal. And so part of it is fostering the community, but also to increase the visibility, because the more it's being used, also being publicly used or visible used, the more the funding agencies are likely to say like, yes, that's a cool project, we fund this. Part is also like to educate and document. I mean, like, it's not just software developer that we need, but we need also educators and people who like technical documentation, because now for the people in the know, it's everything is clear, but we realize that somebody who enters the game late has a harder, steeper learning curve, and we need to get this down. And in the country of the blind, the one-eyed is king, so we need like the people who have a fresh perspective and say like, okay, how can I explain it more adequately to somebody who has never seen this concept? And then the other part, what we do during this workshop is continue on the core library, but also improve the user experiences. That's part of this workshop. And we implemented a certain set of minimum functions to use already GNU Radio, which is largely okay for our purposes at GSI Fair. But we are, for example, not digital communication experts, nor do we try to attempt to. This is the part, if this is needed, that others with that specific domain knowledge should jump in and add their contribution to that. Also, we would like to enhance the user experience, also for non-expert users, and we want to make it as widely accessible via GCC, Clang, and mscripten. And while I think, like Eric once mentioned, is like GNU Radio didn't start out with the UI. So for the people who just want to do signal processing, they're happy with the Python and the C++ script. But I think it's also fair to acknowledge that GNU Radio Companion made a big impact on the community and widened the audience of people who can use and interact with that. We should also look into develop an intuitive default UI to simplify the user engagement with the new GNU Radio 4.0. We have an in-house development for a UI, which is suitable for our purposes, but this, which can rehash and people can take code or steal or take this with no issue. But this code we can't. That's outside of our scope. We can't stem a UI for the whole world. So there's somebody who knows the other domains better, who should provide either an integration into GNU Radio Companion or make a new UI. And there's some long-term performance visions. One is to invest more into SYCL. This is integration of both FPGAs and GPUs. One of the targeted compilers is adaptive CPP, because it's streamlined. It doesn't make a difference whether you run on the CPU, GPU, or an FPGA. Invest also more into developing on microcontrollers like Arduino, because it's a nice, neat tool for educators to say like, hey, that's my Arduino, and you can run a GNU Radio flow graph on it. Why not? And we need to expand the core team to increase the bus factor that's a proposal by involving industry, public labs, and academia, and foster the cross collaboration between different teams. One thing, last but certainly not least, if you want, maybe you all heard about the new White House directive, but this also for the Europeans. There's a new cybersecurity directive in the EU. We have to become more and more compliant with those rules and regulations. And so we have to look into security hardening. That's also the reasons why I think it's important to engage with industry and public labs, because the same requirements that are coming for all NSF or DOE or Helmholtz-funded labs will also come for the industry. So we have to collaborate on that. That's all. I forgot my blue overall, but I say like thank you. And there's like a quick overview on what's happening on GNU Radio 4.0. And I'm looking forward to a technical dialogue. Any questions?
Is this working? Okay. I've got several questions. First of all, the concepts of feedback loops and several connectors pointing into one block is new, but how is this behavior defined? Like, if I have multiple signal sources pointing into one processing block, what is happening in the buffer? Is it just a jumbled mess of data, or is there like a...
The thing is, if you traverse this part of graph theory, because that's the reason why graphs are very powerful tools. While traversing the graph, you can see which blocks you already visited and which port is already visited. So when you see, like now, you have a check in GR3 that you have a loop detected. This is the same algorithm that detects a loop, but instead of saying like, please go away, I can't handle that, we say like, okay, there's a feedback loop and we can calculate what is the latency that you accumulated through the block. And then you prime the input buffer with the default value with the number of latencies that you accumulated. For example, you accumulated 10 samples latency while going through. Then while connecting that port, you select, oh, this path getting here, 10 samples latencies, prime it, so then when the flow graph starts, it has already 10 pre-initialized values on this input and can continue.
Does the user do this or the scheduler? Does the user do this or the scheduler?
That's that has to be fleshed out more specifically, but it's between the scheduler and graph actually, but it's mostly scheduler because the scheduler traverses the graph.
And there was several slides earlier. There were like multiple arrows pointing into one single port.
No, that's for the buffer. That's different. Oops.
Yeah,
you mean this one? This multiple producer, multiple input is mainly for the message ports where you send in one sample. So that's a trivial way how to make feedbacks.
Okay. Next question I have is, you once described the merging of several blocks into one. Is this just possible at compile time, or does this also work from a graph?
We've implemented now for the compile time. We haven't implemented this, but there's also a light version during runtime, but where you can skip the buffers, but you still have the overhead of looping through each of the functions. But most of this is the best performance you get during compile time. That's also reasons why I think it's favorable to look into adaptive CPP, because this is basically just-in-time compiler. So you could say like, give me my flow graph, and then without having to recompile the whole program, you can say like, take this flow graph and then recompile it just in time. There are two paths how to go for it. Either using adaptive CPP, which is like an additional dependency, is basically like a Clang LLVM-based dependency that would be available for the runtimes that can support a compiler, or to spin up a parallel compiler that merges the block and then injects the code during runtime using DLOpen, which sounds dangerous, and it is. That's the reason which we have to see which path we should take. I mean, adaptive CPP, in my view, is more modern and the cleaner approach, but the other way is like dynamic code time injection, runtime code injection, where the compilation time is, you start off with the unoptimized code, spin up the graph in a compiler, and once the compiler says like, I'm done, you replace the old graph with a new merged one.
Okay.
But it's mostly now compile time.
My last question is about the current YAML files. How will they get replaced, or will the YAML files stay? Will they become comments, decorators? Or what happens to them?
We're trying to keep the definition as close or actually identical as possible as the GRC. So the structure will be the same. However, the block names may change. So I mean, in terms of syntax, it will be the same, but the block library may have different names because of the templating. A block that handles floats, a block other than the same processing function that handles float, doubles, or others will be named differently because how they're generated in the back end. Maybe we can there's a way of how to do a translator between GR3 blocks and GR4 blocks, but this is something that we have to discuss upon. What is the better approach on that?
As a block developer, the YAML files stay to indicate what's happening in the companion then? the YAML files stay as like a separate file when I want to develop new blocks for GNU Radio 4.
Yeah, I mean, you can use them the same format.
Okay.
And this is high level. We mostly, at GSI Fair, we mostly worked on the low level part. And then the agreement was like everything that is in the larger ecosystem, where we just very quickly opinionated. We said like let's say for example UI, we said like we can't take a stand and that has to be handled by somebody else. I mean, we know that it's possible, we can wrap everything in Python. We made a strong simplification. I mean, also a big shout out to John Saleh, who made this PMT implementation, because that's the bottom line. So we limited our public API to only PMTs, and that simplified the Python interface because we just need wrappers around the PMT and a few handful of 5, at most 10 functions, and then the whole code base is Python pluggable. But also this Python integration, we made a block where you can execute Python code within the block, but this stringing together using Python, that's something where somebody can rise to the occasion, so like, yes, I flesh it out and make a good Python integration. I played a bit around with CPython, and I find it a bit too scary, to be frank. I know too much about CPython now that I would not be qualified to do this Python integration because I wouldn't be able to sleep in the night. But if somebody else feels more better and has a better idea how to make it smart, please.
There was a question on the YouTube channel about the build time of unit tests.
Yes,
if there's anything we can do about that.
Yes, that's one of the open pain points of GNU Radio 4, because we got rid of the virtual interface that allowed us to be much more runtime efficient, because the compiler can see a larger scope of code that it can optimize. But the problem is that the larger scope also means that the memory footprint during compilation becomes larger. So if you have some compilation units get up to 5 gigabytes of RAM during compilation, and for silly reasons, you try all different possible permutations and see like which one is the fastest, and out of the 100 permutations that computers select, only these two are useful, and it drops all the other ones. We're trying to see how we can further optimize on the templating structure that we use. And we're looking forward to people who have an idea how to make it more efficient without compromising computation performance. But also with Matthias, we discussed it. Meaning the mere fact that LLVM produces the same or sometimes even faster code than GCC in less than half the time, for me points out this is a compiler bug. I mean, like, not that it does produce incorrect code, but if a compiler takes a factor 2 more time for not even faster code, I say like, please. But yeah, I don't know what is the best leverage to, because in the end, the GCC, like GNU Radio, is an open source community where people contribute. There are only a few people who are actually hired to improve compilers. And the question is like how to engage and how to help them to make it faster. I mean, like, I looked a bit into the GCC code. I was scared that our template names, that some of the optimizations are based on string comparison. So you have functions and they do permutations with using strings. And I was thinking like, if you have a type that is only 4 bytes long, like int, float, no worries. But sometimes this templating type, if you have additional attributes, can have up to 1,000 long type names. And then you have to think about, for all the different permutations, it generates this 1,000 times 1,000, you get very large code structures, and that just takes time to process. So I wish I had another life or smart in terms of compiler building. Maybe Matthias can comment on that, what we can do. Yeah, maybe please, if you could hand the mic. Matthias or Ivan, they're much more qualified to explain what to do about compile times.
Yeah, so I didn't find the time myself to dive that deep, but yeah, I've seen especially the template code being so bad, because if you have so many template parameters and then nested template parameters, that on my 4K screen I only see one type printed on the whole screen. That cannot be fast, that cannot be memory efficient. And of course, if you have all these strings in main memory, that just kills your cache performance. And nowadays it's not just only big O notation, right? Sometimes if you're just exceeding your caches, that is sometimes more important to avoid rather than a more efficient algorithm. So all these trade-offs, I think there is a lot of potential to go faster, but it's not necessarily on the side of GNU Radio to solve that. It might be on the side of GCC and potentially also LLVM. I don't know how much they leave lying around in terms of compile time performance there. But again, I would love to go deeper there. I haven't even been able to write a good bug report yet. That would be the first step to do something about it, right? Because typically these things come up with a huge translation unit, and if you want to go to a compiler vendor and say, well, there is a problem, please fix it, you rather want to go with, like, this is a small example that exhibits the problem. Yeah.
Thank you, Ralph. I just had a comment on a question on one of your slides. You showed as a non-developer, as a user question, you showed the difference between single processing and a block processing. So for us non-developers, how exactly does this matter in terms of in an experimental scenario, you have some blocks that you need to process sample by sample, like scaling, that would be quite fine. But if you have a kind of a digital filtering, or you have some block of data, so if you're interested in a time-resolved Fourier analysis, that means you need to gather a couple of frames of data before you can make a sensible, take a sensible information out of this. So in this respect, in this ambivalence, what is the way to go, or how should one really think about implementing such things? Thank you.
Yeah, there's several ways how to skin a cat. I mean, like, you can. Oh, sorry, I shouldn't have said, like, I love cats. There's several ways how to do this. I mean, you can use the process one and then just keep a local copy of your history that you need for doing time-resolved information. Let's say if you need to do an FFT of 1024, you take 1024 and then process it, like for an FIR filter, that would work. But that's also one of the reasons why this process bulk way. So, like, please, whenever you invoke me only once you have 1024 samples available, and then I produce one sample or one spectrum as an output. So that's very flexible. So if you say, like, in terms of blocks, they're functions. There can be single sample in, single sample out. There can be erase of data in, erase of data out, erase in, sample out, whatever combinations you need. There's not a, they're just like these two signatures, either process one or process bulk. The process one is the simpler one, which can't do decimation, but basically with process bulk, all possible mathematical operations, or nearly all, are possible. There was a limitation before, but maybe this is not a limitation with GR4. What type of data you have in or out. You can even transmit tensors. So if you want to do like a laser calculation, a calculation of a laser resonator, you could do it with that as well. Also, you could use it for maybe as a SPICE replacement. I mean, like, we haven't looked into that, but you could also maybe, if you're up to it, just try for the fun of it, make a SPICE circuit simulator with GNU Radio.